Hello everyone, welcome to the fourth video of the MECH to 20 video series. Today we'll be doing another kinetics problem, but this time it'll be in cylindrical coordinates. So let's get started. If the arm OA rotates with a constant clockwise angular velocity of theta dot is equal to 1.5 radians per second, determine the force arm OA exerts on the smooth 4-pound cylinder B when theta equals 45 degrees. Alright, so here I said it's cylindrical coordinates, but it's a 2D problem, so there's actually no z component. So we could just say they're polar coordinates, right? Because we just have an r and a theta, no z. So the first step with like every kinetics problem, I say is to do a free body diagram. And it's gonna be free body diagram of the cylinder B, right? So I have my cylinder here, cylinder B, and I know I have mg is just 4 pounds, and I have, if I look closely, this is where it's good to look at the image closely. Just right pointing straight to the left is going to be the normal force, and at an angle here, right, at an angle here, I have my force that the OA exerts on the cylinder. And since I know that if I have something coming down here and it's at 45 degrees, right? And I know that OA is coming down here. Let's say if this was OA, this is 45 degrees. That means that this here is 45 degrees. And since this is 90 degrees, this is also 45 degrees. If I was to do that, this is also 45 degrees. All right, but let me clean this up a bit. I'm gonna get rid of this. And I'm gonna call the tangential direction is always theta. And the radial was here, right? We had the R. Our arm OB or OA, any way you'd like to call it. It's gonna be like this. Alright. So, and same again here, this is also all 45 degrees. Alright. So if we just start looking at our, let me zoom out a bit. If you start looking at our sum of forces, right? We're just gonna have sum of forces in the r direction is going to be equal to MAR, and I know that is n cos 45 minus 4 pounds cos 45 degrees is equal to the mass here. We want slugs, right? 32.2, so we're going to divide it, and then we're going to multiply by AR. So here we don't know what N is, and we don't know what AR is, right? And just so we're clear on how I got the N cos 45, I just imagine that I'm going to project the components, right? So this would be N cos 45 in the positive R direction. So now we have two unknowns here, and let's go ahead and also do our sum of, let me change my pen. Let's also go ahead and look at what the sum of forces in the theta direction is going to be. And we know we have a theta this time. So it's going to be, we have FOA minus the N sine 45 degrees this time, minus 4 pounds sine 45 is equal to 4 over 32.2 times a theta. So here we still again don't know N. We're looking for FOA. We don't know what that is. We don't know what a theta is, right? So we're looking for FOA, the force that OA exerts on the cylinder. And we need to get AR and A theta somehow, right? So we could get N as well. So right now we have two equations with four unknowns. That's not good. So we have to look at our cylindrical coordinates because we're given what we're told that theta is 45 degrees. We know theta dot is 1.5 radians per second. So we have theta equals 45 degrees, theta dot equals 1.5, and taking the derivative of theta dot is a constant, so it's just going to be 0. And now we could get our components, right? We know R. So here I have a triangle, right? Basically, this is R. I know this is 45. This is 4, 45. This is my R. This is 90 degrees. So I can get that R is going to be doing SOHCAHTOA 4 over cos theta. And I'm going to rewrite that for secant theta. You'll see why in a second. And evaluating that at 45 degrees, I have 5.657 feet. All right. Now I need R dot. How am I going to get R dot? I have to derive. I take the derivative and I get the derivative of 4 over cos theta. It's more challenging, so that's why I put it as 4 secant theta, because I know I'm going to have to take the derivative anyways. So I get R dot is equal to 4 secant theta tan theta. And keep in mind, we're taking the derivative with respect to time. So we have to do chain rule because right now we just took derivative with respect to theta. So we have to do chain rule and we get the derivative of theta is theta dot. So if we evaluate that theta as 45 degrees and theta dot as 1.5, we get R dot equal to 8.485 feet per second. So now I need to get R double dot, and this here is the tricky part because we have to do product rule twice. So I'm going to take the 4 out and I get doing secant theta tan theta, and taking the derivative of theta dot gives me theta double dot, and then I'm going to take out the theta dot and I'm going to take the derivative of secant theta tan theta, but that's just another product rule, right? So I have secant theta, and I'll move it here for now. Secant derivative tan is secant squared theta, and remember chain rule, so I have another theta dot, and now I'm gonna get tan theta, and then the derivative of secant is secant tan, and again chain rule, so I have another theta dot. Don't forget the theta dots. It's a common mistake to forget that you're taking the derivative with respect to time and you forget to do the chain rule, but that's going to give you the completely wrong answer most of the times. So here we know, when we evaluated, we know that theta dot, this is just going to go to 0. So I'm just left with 4 times theta dot and all that. So evaluating that with theta at 45 degrees, theta dot at 1.5, it's going to give me 38.18 feet per second square. Alright, so now that I have all my variables, now I can get what my AR is and what my A theta is, right? So from the formulas, we know AR is equals to R double dot minus R theta dot square, and we know that A theta is R theta double dot minus 2 R dot theta dot. So AR, if we plug in R double dot minus R times theta dot square, I get 25.46 feet per second square. And for A theta, this goes to 0 because theta dot double dot is 0. I get 25.46 feet per second squared as well. So same thing. So now since I have AR and A theta, I can plug this in to my equation. And just to show you what AR and A theta look like, I'm gonna have AR going out here, and I have A theta going tangentially over here, right? So now that I have those, I can solve for n, and I get that n is equal to 8.472 pounds, and plugging n into here, plugging n into the F theta equation, and plugging A theta as well, I can solve for FOA, and I get that that is equal to 12 pounds. So let's see if we answered the question. It asks for the force that arm O exerts on the cylinder. That is exactly our answer.